Okay, so perfect. So let's get started. So last lecture, I talked about regression with linear models. So I just go through it very quickly. So we have a model. I talked about all these things, the regression with the linear model. And then a few slides later, we talked about the concept of the loss function and the cost function. And that we said that we want to minimize it in order to find the best weights. So also I talked about the vector notation. Regarding the minimization, we have a direct solution, which we can solve where we can take the derivative of the cost function and make it equal to 0. And if the result would be something like this, that we have, this would be least square solution. Then another topic was how we can go beyond linear functions of input space. Like if you want to fit a function like this to this curve, what should we do? And we talked about the basis expansion and as the way we can do it. So polynomial expansion is one, but there are a lot of different basis expansions. So we talked about underfitting and overfitting of the model. And as a solution, we talked about the concept of regularization. So regularization basically pushes the weights towards 0. And that's a way to encode our, say, prior knowledge about what's the good solution should be before seeing the data. We talked about the L2 penalty and also L1 regularization. So L2 would be the result would be ridge regression. L1, the result would be lasso. So this is the lasso. And then I think the last thing was a kind of this geometric view or constraint formulation of this regression and ridge regression and lasso, which the difference was whether the constraint set was L2 defined by the L2 norm or L1. So I think that's that was what we did last time. And today we wrap up the regression by providing a probabilistic interpretation of what this loss is doing, the L2 loss or squared error loss. And then we move towards classification. But also in between, before that, I talk a little bit about optimization using gradient descent. And at the end, I talk about stochastic gradient descent if we have time. Okay. So we use L2 squared error as a measure of the loss function, as a loss function for regression. So the loss function was something like this, and we had the L2 error between what the model predict and the true value as the loss function. So the question is that why we chose that. I mean, that was reasonable. Many of you suggested that we should do that. And kind of the loss looks very natural, but I mean, you may ask why that's a good solution. So there are at least two answers for that. So one answer is that we can have a probabilistic perspective for what this squared error loss is doing. And then there is another justification, which I will talk about in the next lecture on bias and variance decomposition. So the probabilistic interpretation has this kind of assume that the model or the data comes from some model, some probabilistic model. So what is the model? Let's go through it kind of, and see how it works. So suppose we have a model that basically takes inputs, xi, for example. So I give you, or I give the model xi, then multiplies it by some weight, w. So this is a linear model, and add some noise to it. And what is the noise? So the noise is like a normal distribution or a Gaussian distribution with the average or mean of 0. and a variance sigma squared. So this is the model of the noise. We add the noise to the input, or W transpose times input, and that gives us the value of Y. And the noise, we assume that is independent of the input Xi. So the process that Xi is generated is independent from the process that the noise that contaminates the output is generated. So we can say that the distribution of Yi conditional Xi is some normal distribution with the mean of W transpose Xi plus variance sigma squared. So this is the probabilistic model of how data is generated. For now, we assume that this is how it is. And if that's the case, then we see that squared error loss is essentially if we follow the maximum likelihood estimation process, we get to this squared error loss. So how many of you remember maximum likelihood estimation from your statistics course? Some of you. Okay, so probably half of you. So I briefly go through it. So suppose that we are given, I'm going back one step, but this is kind of tailored to this setting. Suppose the input data Xi, X1, X2 to Xn are given, and the outputs are independently drawn from some distribution. So the distribution is a function of Xi and some weights. And then based on that, we get some sample TI. So these targets are generated from this probabilistic model. I haven't specified what this P is now on this slide, but we will see on the next slide that one of the choices is the choosing it as a normal distribution that we have here at the bottom of the page. If we do that, we get certain solution, a square error loss. But on this slide, I'm not talking about Gaussian distribution already. Okay, so we have an unknown parameter W. And so the data set that we get is an n bunch of data points, inputs X1, target T1, up to Xn and Tn. So the likelihood function, the concept of likelihood function is the probability of this data set is generated condition on that one particular choice of weights. So we don't know weights, but we can try different weights and then compute the likelihood of this data being generated by that W. So this is the likelihood. Maximum likelihood estimation is a process which is based on principles. So we can think of it as it's a principle that suggests that we have to find a parameter W hat, estimate parameter W hat that maximizes the likelihood. So essentially, you can think of it like this, that we have a probability of data set which depends on W. For different Ws, we get different probabilities. Maximum likelihood estimation, MLE says that choose the one that maximizes this likelihood, because that's the most likely parameter for generating that data. So the concept of the maximum likelihood estimation is that it's like after observing the data samples Xi, Ti for n data point, we should choose W that maximizes the likelihood. So that's the MLE. So let's go into a bit of detail and see for our specific case of probabilistic model, how it would look like. Maybe before that, I guess we can do a little bit of simplification. So this slide is again not about our specific Gaussian model. So assume that the data are independent. So Xi's are independently generated. So the likelihood function of samples D is a product of their likelihood, because probability of two random variables, if they're random variable, say Z1 and Z2, if they're independent, would be probability of Z1, probability of Z2. And we can do it for n data points. So here is a conditional probability, but we are saying that probability of T1, T2 to Tn, the targets, conditional inputs, and the weight is the multiplication of the probability of Ti's, conditional xi, and w. So w is shared, but we can kind of decompose it to multiplication of each of the probabilities. So this would be our likelihood function. So if we want to maximize it, we can try to maximize this term. But maximizing the product may not be very easy or numerically stable. So we can also take what we do, some numerical simplification. Simplification is that we take a logarithm of it. And then if we take the logarithm, it becomes what? The product becomes summation, right? So we compute the log of it, and the two objectives are equivalent since logarithm is strictly increasing. So it's essentially logarithm just stretches things, but doesn't change the order of where the maximum happens. Also, instead of maximizing the likelihood, we can minimize the negative of log likelihood. So maybe the step is like this: maximizing likelihood is the same as maximizing the logarithm of likelihood, which is the same as minimizing the negative of logarithm of likelihood. So that's a kind of middle step. So negative of log likelihood would be minus of logarithm of likelihood, which would be minus log of the product because of independence, this is step, and log because of property of log. This becomes summation of log of P of Ti, conditional Xi, and W. So the result is that maximum likelihood estimation would be after observing these data sets Xi, Ti for n data points that are sampled IID, independently and identically distributed. Then the MLE would be minimizer, or the solution that MLE provides is the minimizer of this minus sum of log of P of target condition on input and one particular weight. And we just find a weight that maximizes or minimizes. So is this clear? Any question? Okay, that's good. The rest is just, we use this model that we have here. This Gaussian model, just expand it, and then compute this log of probabilities. So now we suppose that the model is, again, what we assumed a few slides ago. So it's a linear model with some Gaussian noise. So this is the Gaussian noise with mean zero variance equal to sigma squared, which is independent of anything else. So this is sigma noise I is independent from noise J, and also noise I is independent from input I, Xi. So if that's the case, then our model would be P of Yi condition XIW would be some constant, which depends on variance of exponential of minus 1/2 sigma squared of the difference between Yi and W transpose Xi squared. So this is would be our probabilistic model or the probability of observing Yi condition it is Xi and the weights of that. So if we compute the log of it, we get a term which is minus 2 sigma squared, minus 1/2 sigma squared times Yi minus W transpose Xi squared, minus log of 2 pi sigma squared, the whole thing under square root. So now we compute maximum likelihood estimation of this. So we just plug this here, and the result would be the MLE would be argmin of the summation of squared errors multiplied by 1 divided by 2 sigma squared plus some constant, which does not depend on W. I guess what is important here is that C and sigma do not depend on the weight. So in the optimization, it doesn't really matter what their value is as long as sigma is non-negative, non-zero. So if we see this, so what does it look like? Does it remind you of anything that you've seen before? I mean, I wrote an answer down there. The loss function that we had for regression, squared error loss function. So this is exactly squared error loss function. Oops. I mean, the only difference is that the constant there was 1/n, for example. Here is a different constant, but it doesn't matter. So yes, there's a question.
How do we get from having y's to having t's?
So that's a good question. So essentially, this model says that for one particular any y, that's the probability. But now here I'm replacing the y with the t that we observed from data. I mean, I guess in some notes or some notebooks, for example, probably they use the same y's, but I just wanted to differentiate between a generic model, probability over y, versus particular instances of outputs, targets, that we denote with t here. So that's one. Right, yes, so on the chat, it's list the squares, you answered that. Yes, so this is the loss function that we defined. Okay, so that's the thing. Okay, so there's actually a good question. So there's a quick question asking why assuming noise is Gaussian distribution and seems to be arbitrary. So yes, so this is exactly why here the assumption that this noise is coming from a Gaussian distribution seems a bit arbitrary. I mean, there is an answer in the chat that says that we have central limit theorem and things like that. So that's true. Gaussian noise appears a lot in the nature, and that's why having Gaussian noise assumption is a reasonable assumption. But this is true that here, based on this assumption, we got this result. If our noise assumption was something different, we might get some different results. So I guess that's one point. But the other point that I want to kind of emphasize is that squared error loss is a reasonable loss, even if the noise model that we have is not Gaussian. The interpretation is not this exact interpretation that I have, a probabilistic interpretation, but still it has some nice properties. And that would be exactly this other comment. There are other justification too, that we get them in the next lecture, which shows that even if the Gaussian noise model, if the noise model is not Gaussian, we still doing a squared error loss is a reasonable thing to do. So I guess this is one point actually people, I guess you should be careful that people may say that squared error is just working for Gaussian models. This is not true. This is for Gaussian model, it has a maximum likelihood estimation interpretation of a model with a Gaussian distribution. Okay. Oh. So I briefly talked now, we talked about something unrelated to regression for a while. So gradient descent for optimization. I think you have seen it in the tutorial, like how optimization based on gradient descent can be done. But let's kind of briefly review it and make the connection to what I talked about so far. So the first, if you remember, we had at some point, we get to the loss function several slides ago, and I mentioned that now we have to find a way to optimize it, find a solution that minimizes that cost function. And one solution was a direct approach, which was taking the gradient, make it equal to 0. But then another approach is based on minimizing the cost function using some iterative approach, which would be a gradient descent in this case. So, and actually, I think a few of you suggested that gradient descent would be a good solution to solve it even at that point. So this shouldn't be very surprising, and you have seen similar things probably in your other courses or projects. So gradient descent is an iterative algorithm. It's an iterative algorithm which applies an object repeatedly until it converges to some point or some criteria is met. So the way it works is that the initial weights W's to some arbitrary reasonable value. For example, maybe we can choose all of them equal to be 0. And then repeatedly adjust them in the direction of steepest descent, in the direction of gradients. So the idea here is that, I mean, this is, I guess, probably very simple. You know it from calculus. But if you have a cost function and we compute its partial derivative with respect to Wj, if that partial derivative is positive, then increasing Wj a little bit increases J a little bit. And vice versa. If it is negative, then increasing Wj decreases J. So what we want to do is to decrease J, like minimize the cost function. So essentially, if we compute the partial derivative of J with respect to some Wi, for example, to not be confusing with the other J, if it is positive, then in order to decrease J, we just go decrease the Wi's. So the cost update rule would be like this. Wj would be Wj minus alpha times partial derivative of cost with respect to Wj, which essentially for the case of our cost function for regression, squared error cost loss function, it would be Wj minus alpha divided by n times the summation of yi minus ti times xji. So this would be essentially the update for weight Wj. So the one thing that is, I think, is important here is that alpha I, this alpha I here, is called the learning rate. And the idea is that if it is larger, the faster W, the weight changes. And if it's small, it changes slowly. So I will talk about it a bit later, but the idea here is that this is a hyperparameter of your learning algorithm, and by tuning it, you get desirable behavior. So this was for only partial derivative with respect to one of the weights. If you compute with respect to all the weights, this would be the gradients of cost with respect to W, which would be the partial derivative of cost with respect to W1 to all the W's, d-dimensional dW's. And this is the direction of fastest increase in J. So we can now write the update rule for gradient descent in the vector form. We say that the vector of W, which is a d-dimensional vector, should be updated as W minus alpha times gradient of J with respect to W. And if you write it for our cost function, it would be W minus this summation of yi minus ti's times xi. So just note that yi minus ti, what's the dimension of it? Sorry, what's that? N by 1 vector, d by 1. Is it? But what is yi? Is it vector or scalar? Yi. This one. Wi is scalar, right? And ti is also scalar target. So this whole thing should be a scalar. But xi, what about xi? That's a vector that is d by 1. And W was also d by 1. So it's a d-dimensional vector. So essentially, we multiply scalar which says how far our y, the predicted y, is from the target t. So if they are close or far, and then based on that, we scale xi's to that amount, and then add it. And this is only for one of the i's. For the cost, we need to have summation over all the weights. All the data points. We have n data points, and then we multiply. So that would be our gradient of the cost function. We multiply it by learning rate alpha, and then subtract it from the current rate. There was a question.
Sorry, I have a question. This form of the gradient, is this specific for these squares?
This one or here?
That
Second one. Yes, this is for listed squares. Yes, yes. Yes, but so yes, I guess this top part, this is just gradient descent for any cost function, and we will see if we had another loss function, it would take a different form when we go to the second line.
Yeah, but the second line is down.
For square error. Yeah. Okay, so yes, there are correct answers here. There are scalar. Okay, perfect. Okay, so the other thing I guess that is kind of worth mentioning is that if it converges and when it converges to a point that is a critical point. So the gradient of J is equal to 0. Can you give me an intuition why that is the case? Like why doesn't it converge to a point that this gradient is non-zero? No.
The only way you're update rules and stop changing stuff gradient is 0.
Right, yes. So the answer is that the only point that it may converge is when the gradient is equal to 0. If it is not 0, it would keep updating the weights, right? Because if this is, say, if this term is non-zero, I'm adding some non-zero vector multiplied by alpha to W. So previous weights and the current weights should be different because of that. So it is not converged. What does convergence means is that it is not exact. Two W's are exactly the same. In practice, it never converges to a point that it doesn't change at all. But we will talk about it. So there is a question. Is there a question in chat? No. Okay, so raise hand at some point. So this is gradient descent. So even if we have a linear regression where we have a direct solution, sometimes we may want to use gradient descent. I mean, there are a lot of reasons. I guess one of the reasons that gradient descent is a very generic approach. We can apply it to different loss functions, including for the linear regression with the squared error loss. So if you have an optimizer that implements gradient descent, we can just use it, the same generic optimizer for our linear regression model too. But also, the other kind of reason that we can think about is that if the dimension D is high, then maybe gradient descent can be computationally more efficient than the direct approach. To see why, just consider what was the linear regression solution. So it was X transpose X time inverse times X transpose T. Just focus on the inversion part. So, okay, maybe X transpose X. Do you remember what was the dimension of it? D by D, right? So the dimension of X transpose X, the dimension is D by D. So when we want to compute the inverse, we need to compute the inverse of a D by D matrix. So what is the computational cost of inversion of a D by D matrix? So
Big.
D.
Well, big if D.
So the answer is D. So no, if I give you D by D matrix, if
No, sorry, I was saying big.
okay, right. Any other answer?
Well, those are there.
Cheating by saying.
Sorry, say.
I feel like cheating by saying.
Well, actually, this is a bit cheating, but actually, not really. That's not the best solution. That's why I was wondering. This is so D cubed is, as I have here, is the cheating solution, and that's the standard. Many numerical methods or optim packages has that cost, but that's not the best computational cost we have, and that's why kind of wondering whether you know what is the best. So the best is, I'm not sure the exact value, but this is a kind of, finding the best is an open question, I think, in computer science. But I think the best that we have in theory is, if I remember, is 2.30 something, maybe 37 or something. So it would be D to the power of this value, order of that. That's important, that's the order of this. But these algorithms are not practical. So you can, if you implement this algorithm, that wouldn't be faster for any matrix that you face in the usual situations. But this is open, that what is the smallest exponent that we might have. But for practical purposes, it's D cubed. And so the case is, so I mean, okay, so what's the reasoning? But for gradient descent update, the cost would be n order of n times D. So n data points times D dimension. If you remember, there was, so we have, let's try another color. So we have summation over n here, and each of them is a vector, D-dimensional vector. So we are more summing n of D-dimensional vector, so the whole cost would be n times D. Okay, so, and if the dimension is very large, then it is possible that D cubed is going to be much larger than n times D. Of course, it depends on the number of data points entered. Okay, so another thing is that another point that I want to mention is that, okay, so this is the gradient descent updates. If we use a regularized, sorry, is there a question? Yeah. Right. So the question is that how do we guarantee that we go to the only the global minimum instead of some other local minimum? That's a good point. Here in this setting, the linear regression with this loss and that model, linear model, the cost function would be convex as a function of the weights. And basically, if a function is convex, if this is the weight space, you always converge to its minimum if you converge to global minimum. But if the function is non-convex, then there might be more than one local minimum. But for this case, because the function is a convex as a function of W, then that would be unique. Okay, so there is another question, okay, on the chat, I think. Yes, would you? Can you ask your question?
Yes, so my question is, when we want to reason about the computational time of gradient descent versus the optimal solution, how can we reason about the number of steps that the gradient descent has to take? Because we know the cost for each step, but like we don't know anything about how many times we have to update it.
Yeah, that's a good point. So that was this cost. This comparison is one step of finding the solution. Like in this D cubed is the cost of finding the solution after multiplying with other matrices. But this is only the cost of, as you pointed, is the cost of one step. We can talk about the convergence rates of gradient descent getting to the point of epsilon accuracy of the optimum, and the number of iterations required for that. But I haven't really talked about that. So, but yeah, I guess that's a good point. This is only one iteration of it discussed, but we need to have maybe tens of or hundreds of iterations. And how many iterations we need to get in order to get to epsilon neighborhood of the optimum, the global optimum. That's another factor which is kind of skipped. Probably one of your reading assignments will be about comparing the computational cost of these different optimizers and what is the best for in a machine learning context. It wouldn't be a comparison with gradient with a direct solution, but comparison between stochastic gradient descent and this gradient descent that I talked about. Okay, thanks. Okay, so another thing is that if you have a regularizer, what happens? And so essentially, instead of J, we have J plus lambda times regularizer. And if we write this regularizer, compute this gradient, if the regularizer is L2 norm, so it would be L2 norm squared, we get some results like this. So I think I need to have, and then if I kind of simplify my equation, the right-hand side, it can be seen that we have this interpretation that I have 1 minus alpha lambda W minus alpha times gradient. And this term can be interpreted as some form of decaying the weight, because just imagine for now that this gradient is equal to 0. So what happens? Like W is not 0. Suppose W is at some step, WK is, I have WK. WK plus 1 would become 1 minus alpha lambda WK. So you see that the size, if this thing is smaller than 1, then the size of WK plus 1 is kind of becomes smaller than WK. So we can have a weight interpretation that it is doing some form of weight decay. Okay, so another comment that I have is about learning rates or step size, that alpha. So if alpha is, so here what I've shown is the level sets of the cost function. So this is for some arbitrary cost function. It's kind of for visualization only. So what may happen if, so this is the minimum, global minimum here, or local minimum. I mean, for squared error loss and linear model, it would be global. And here, this is the point that we start. And then you see after several steps, we get closer to the global minimum. But the point here is that if alpha is very small, the progress might be very slow. So it takes a while. So if alpha is large, so what happens is that at this point, we move in the direction of minimizing the cost, but we go a bit too far. So we go to this point that is kind of actually not very small. And then again, we go in the direction of minimizing the cost, but we make a big jump. So as a result, you might observe some oscillatory behavior on our weights. So it may not converge. Another case is that if alpha is too large, we actually might observe in some cases that the sequence of weights are actually divergent. So they don't even oscillate, but they just become larger and larger. So this is, again, depending on the size of the alpha. And this can be analyzed, like what range the alpha would be stable for one particular cost or not. So there's a kind of heuristic. I mean, this is saying that alpha should be something between not too small, not too large, but when you want to do it in practice, you probably need to try different values of alpha. We treat it, as I said, as your hyperparameter and see which one gives you a better and nicer performance. I mean, you can, finding divergence is easy. Like you see that your weights are becoming larger and larger. Oscillatory behavior also you can kind of observe. But yeah, so I think the point is that you need to have a grid point like 0.1, 0.03. I mean, these are kind of arbitrary numbers that I wrote here, but it seems to be a kind of reasonable range. And I guess another visualization is if you, when you are training your algorithm for not only for these linear models with squared error loss, but in any model. So you have it, you should plot your training costs versus iteration. And then if you see a behavior like that, this is going down, that would be good convergence behavior. If you see that it is going down, but very, very slowly, maybe your learning rate is a bit too small. And if you see that it is going up, then probably it is too large. Okay, so this is kind of like a slide for summary of some basic notations. We can skip it. Another, I guess, point that I want to mention is we already talked about vectorization. It makes the notations much simpler and nicer to write everything in form of matrices and vectors, but also computationally for languages like Python, that would be much faster if you write things in a vectorized form. So if you write with C or Fortran, doesn't matter. But if you write with Python for loops in Python, like if you write it like this, would be very, very slow. But if you write it in the form of matrices and use packages like NumPy, and you write like you want to multiply W and X, you write it as a NumPy of dot of W X plus say bias, that would be much, much faster. So I think in your homeworks, in the future, you shouldn't use, I mean, you see that it would be very slow if you need to use for loop. So you should try to avoid it as much as possible, especially for things that can be written in this vectorized form. So yeah, I guess I mentioned these things. And I guess maybe the other thing that would be important is that if you have matrix multiplication, it can be actually very, very fast, like much faster than you run on CPU if you run it on GPU. So GPUs are basically optimized to run something like matrix multiplication much faster. Okay, so that was regression part. Any quick question? Okay. So now let's talk about classification with linear models. So the story is very similar to the previous case, the regression, except that here, instead of having real value targets, we have a discrete set of targets. So in binary classification, essentially we have either true or false, or 0 or 1, or plus and negative. So these are the possibilities of our value. So we want to predict a binary value target. So for some examples would be that predicting whether a patient has a disease or not, given some inputs that we have the presence or absence of various symptoms. So that would be an example of binary classification, or classifying an email as whether it's spam or not, or whether there was a fraud happening or not in some financial transaction. So these are just examples. You have already solved one homework assignment with classification, so you know what the problem is. So here, again, going back to this model, we have an input, we have an output that is processed through some model. And then we need to talk about targets and how different the target is with respect to our prediction Y. And that is encoded by loss. So we use essentially the same model as what we had in the previous part on regression, but then because now we are talking about a target which is discrete value instead of a real value, we need to rethink how we should choose the loss function. So a big part of this, the rest of this lecture is about this, the loss function aspect of it. Let's try to formalize it a little bit. So suppose it's a binary, predict a binary target which is equal to 0 or 1. So we say 0 or 1 as our possible targets. Another name for, sometimes we say that t equal to 1, we call it positive examples. If t is equal to 0, we call it negative examples. And also another thing is that the choice of 0 and 1 is arbitrary, of course. We could choose it at some other value, for example, negative and positive, like -1 and +1. I think sometimes for kind of computational or for computational convenience or having a more nicer formula, we use we assume the targets are -1 or +1. Sometimes we just assume that it is 0 and 1. So it would be clear from the context. So this is the targets. So either 0, 1 or -1 or +1, or we just call it positive or negative. The other is about the model, and the model is the same as before. So the model is that we have input X, we multiply it by W transpose, and then we add some bias step. And how do we convert the model to a classification output, or we have a classifier, we want to decide whether it should be positive or negative output, we use a threshold. So we say that if Z is larger than some threshold, the R, the output would be 1, otherwise it would be 0. So I guess this step is kind of important because we want to predict something that is, say, 0 or 1. Output of this box should be 0 or 1, or -1 and +1. I mean, depending on the case. But this linear model, when you are multiplying vector W, which is real value, by some other real valued X, that would be some real valued output Y, the Z here. I'm denoting by Z. So in order to convert a discrete value, we have this thresholding process. Yes.
Is there a threshold hyperparameter?
The threshold? Actually, in the next slide, I'm going to get rid of the threshold. So it could be a hyperparameter, but we are getting rid of it, so we don't have to worry about it. But this is essentially saying, if Z is larger than 10.5, it would be 1. But to simplify things, I mean 10.5, why 10.5? Okay, so we want to eliminate the threshold. We assume without loss of generality, that threshold is equal to 0. So then the question W transpose X times plus B being larger than 1, we just write it as W transpose X plus B minus R, and consider this whole value as W. So this is one parameter that we have to learn. But then the threshold becomes 0, and then we are saying that when this model, the linear model, predicts something positive, then class is positive. If it is negative, the class would be negative. Also, as we had seen before, we can eliminate this bias term, this term that is here, by just adding a dummy feature x0, which is always taking the value of 1. So if you remember, we had this thing for regression too. And as a result, the model becomes essentially Z equal to W transpose X. And our prediction would be whether Z is positive or negative. If it's positive, we output 1. If negative, we output 0. In some cases, if we want to predict, instead of 0 and 1, we want to predict -1 or +1, the only thing that would change here is that we need to have -1 as the prediction here. So nothing major. Any question? Okay, so there's a, there's a question that doesn't this threshold function make the differential of the function meaningless? Yes, or 0 everywhere except one undefined. Yes, so that's true, and I'm getting to that. So, yeah, threshold function has a bit of problem. Okay, so I'm quickly going through a few examples of kind of artificial examples showing that how what this linear model can represent. And so now the concern is not about the generalization, and we just want to learn a Boolean function. So assume that inputs are Boolean, and we want to predict some function like and, not, or XOR of these inputs. So what is not? Well, all of you know, if X1 is 0, the target should be 1. If X1 is 1, the target should be 0. And we also added this X0 as the bias term, the dummy variable that deals with the bias. So it's always 1. So consider this is our training set. So we know that for 1 and 0, the input 1 and 0, the target should be 1. 1 and 1, the target should be 0. So we want to find a linear model that takes these x's and outputs the same as t. Okay, so what are the conditions? Now we want to find, so remember, so the model was W transpose X. X is 2 by 1 here. So we need to find 1 by 2-dimensional vector. And then what we need is that just basically, what we do is that basically put this inputs and try to find weights that satisfies our requirements. So when X is equal to 0, X1 is equal to 0, what we need is that Z, okay, what do we need? Well, we need that Z to be positive, right? Because, so I'm talking about this case. If X is 0, we need our classifier to predict a positive value. So Z should be positive value so that after thresholding, it gives us +1 as output. So what we have is that Z, what is Z? Z is W0 X0 plus W1 X1, that should be positive. So X1 is 0, so this is 0. So this term doesn't matter then. So what we have is W1 X1 should be 0. Okay. Right. Yeah, X1 is something happened. Okay, so this is 0, right? And this is 0. Okay, so that's, thank you. So so we can ignore this term. So W0 times X0, which is 1, should be positive. So this gives us a condition that W0 should be positive, right? And Fx, when X1 is equal to 1, so the second case, we need again Z being W0 X1. So this is 1, this is 1. So this gives us W0 plus W1 should be negative. So these are our constraints. And as long as we find W0 and W1 that satisfy these two inequalities, we have a model that predicts the right targets. One possible solution is that if we choose W0 is equal to 1 and W1 equal to -2, we can verify that. The question is that, is this the only solution or not?
No, we multiply the weights by some positive values.
Right, so the answer is that no, if you multiply the weights by positive constant, then we get also the same solution. So I guess that's an important thing. The solution is not unique. So this is one of the many solutions. So let's try another model. We want to kind of classify and. So if we have, so x0, this is always 1, x1 and x2. So 0, 0, it should be 0, 0, 1 should be 0. And the only case that it should be non-zero, it should be 1, is that when both of them are 1. So if we just write these equations, so we have z is equal to w0, x0, w1, x1, w2, x2. So if we just write each of them, our requirement is that w0 should be negative, w0, w2 should be negative, and w0, w1, w2 should be positive. So again, one possible solution is these values. Okay, so this was a kind of algebraic manipulation. We got some possible solutions, but we can also have some geometric interpretation too. Maybe it would be good to have a quick break now. Maybe it's 10 past 12 now. Maybe we can start in 3 minutes. Okay, so here we can also look at these things in the input space or data space for the not example instead of algebraically. So what's basically visualizing here is that saying that if we have, we have a kind of this diagram of that has x1, x0 and x1. I put positive and negative examples on this figure, just using plus and minus in order to indicate something is positive or not. So for example, when x0 is 1, x1 is 0. So this point, it should be positive 1, should be positive value. And when both of them are 1, this would be this case, which is negative. So what we want to find essentially, we want to find a line that on one side of it, thinks the value of the line equation is positive, and on the other side, the value would be negative, because that's how the threshold function works. So effectively, we want to find a line like this. Maybe use a different color here. So this line, that one side of it, things are positive, and another side, the values are negative. So to kind of make it a bit maybe more clear, so here we assume that we have a linear model, right? So weights or hypothesis W can be represented by these half spaces, which are basically saying that we have the set of x's where W transpose X is positive, and we have set of x's where W transpose X is negative. So one side of it, so you see that this is W transpose X is defining a line here. So we have a W transpose X. This is a line W transpose X is equal to 0. One side of it would be values that W transpose X would be positive, and the other side of it would be W transpose X would be negative. So here, this would be our H plus region or half space, and here would be H minus half space. So, so that's the kind of idea that we can have in this case, there is this line that divides these two regions. And our goal is to find a line essentially that separates the positive cases and negative cases. The boundary, as I've shown here, so this line is a decision boundary. And the equation, the algebraic equation for it is W transpose X being equal to 0. So both sides of it basically, each side of it has a different classifier because we are thresholding at the value of 0. And in this two-dimensional case, when we have X x0 and x1, we are essentially having a line. But in general, this is a plane or a hyperplane. Like for 3-dimension, it would be a plane. In more than that, it would be a hyperplane. So that hyperplane would be our decision surface, and two sides of it would be cases of positive or classified as positive and negative. If we can find a line or a hyperplane or linear decision kind of rule that separate data perfectly, like on one side everything is positive, on the other side is negative, like what we have here, we say that data is linearly separable. But it is possible that we cannot find a hyperplane that separates the data perfectly. Yes?
I wonder how do you know the lower part is H class?
Oh, so this is just for visualization. I mean, depends on your choice of W, right? So if you choose, depending on W, one side of it would have positive values, the other side of it would have negative values, right?
Okay.
So here, assume that this is the right weight, so that one side of it would be the correct side has a positive value. Maybe another example, maybe suppose I get this equation, but define a new W prime, which is minus W. So W prime transpose X, it also defines the same line, but the order of whether something is positive, one side is positive, the other side is negative, would be flipped. If we choose it correctly, it would be the bottom side would be positive. And I assume that for sake of visualization, that was the case. Okay, so we can also look at these things in the weight space. So we had it, if you recall, like I guess many slides ago, that we can have a data space, we can have also weight space. So data space essentially has x's, x0 and x1, but also we can kind of find the mapping on W0 and W1 on the weight space. So what are the constraints that we have? So I think from a few slides ago for the NOT case, the constraints that we got was these things, that W0 should be positive, W0 plus W1 should be negative. If we visualize it in this figure, then we see that there are okay, it doesn't erase now. So we see that we have a line or a half space defined by this inequality. W0 is equal to being positive, which is this green which is defined by this region, right? And then we have W0 plus W1 being negative, which is defined by this line here. So you see that we have one region that is for one inequality, which comes from one of the data points, satisfying one of the data points for the NOT case. And then the other one comes from another inequality that comes from the second constraint from data points. So in order to find the weight that satisfies all the constraints that we have, we need to find a point that is at the intersection of all these constraint sets. So what would be the intersection of it? So something. So we have this region, and we have this region. So what is the intersection of them? It would be this region that is kind of shaded here. So if we choose a weight in that region, then that would satisfy our classification constraints. So this region is called feasibility or feasible region. If this region is non-empty, then there exists, the problem is feasible, and there exists a weight that classifies our data point perfectly. But if that region does not exist, the problem would be infeasible, and so that, and we can't classify all data points perfectly. Is this clear?
So just a clarification, the shaded part will be the feasible region.
Sorry,
Feasible region, the shaded one.
Yes. The shaded one is the region that if we find a vector that classifies, that satisfies both of these constraints, which means that the linear model that we find after thresholding is classify the data points perfectly. So I guess there's some discussion on chat that seems to be more or less resolved. Okay, so I try to be a bit faster. So and example requires 3 dimensions, so including the dummy one. So its visualization might be a bit more challenging. So with the weight space also would become 3-dimensional. So what we can do is that look at some certain slice of it, like 2-dimensional slice of it. But the whole idea is the same. So we can talk about data space, which basically says that for and we have negative, 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 and the only positive case is that when both x1 and x2 are +1, which would be this green point. And then the linear classifier would be this line here that we have here, which would be a plane in 3 dimension. Now this is only a slice that we're looking at. And then we can have the same, we can look at the constraint sets and see what are the feasible region. And we see that the feasible region is only this one, the shaded region. And any point there would be a correct solution. So maybe I think this is actually a good exercise. We go through this slide and kind of verify that these constraints are actually what we need. But then there are other cases that, for example, if you have XOR, we can't, which basically says that if one of the X's are positive, and only one of them, then the output is true or +1. Otherwise, if both of them are 0 or both of them are 1, then it wouldn't be, it would be 0. So you see that in this case, I mean, you can kind of convince yourself that you can't find a line here that separates all these 4 points. Like if we find like any of these points, any line that I draw here, none of them can satisfy our case. And it can be proven, so it's not super difficult, but it's not very important in this case. I guess this is intuitive enough. So now the question, okay, so we get to some geometric understanding of what is happening. So we have a bunch of points. Our classifier essentially has a linear decision boundary, which is defined by a hyperplane. For some cases, for some problems, we can linearly separate them. For some of them, we cannot. For and not, we could. For XOR, we cannot. Now, of course, the question is how to find those weights. So we have this linear model. The question is that how we can find W and B. If training data set or training set is separable, so there exists a solution that we can find a line, then we can solve for W and B using linear programming. And now I guess the question is how, but I'm going to skip it and let you think about it. But I think I'm going to talk about it in maybe 2 lectures. Just mention it. That's not going to be the main solution that we have. But it is good to, I think it would be a good exercise for you to figure out how you can write it as a linear program. And if you don't know what linear program is, I guess it's enough to check Wikipedia. But you don't need to actually go into detail of how to solve linear program or things like that, just at a very high level. But then if the data is not separable, the problem becomes harder. We can't use the linear program, and then we need to use other approaches. And also in practice, never data is separable. Okay, so what we want to do is that instead of trying to find a perfect separation of data to +1 or -1, we want to find a classifier that minimizes the number of misclassification, the incorrect classification on our training data. This is something like we did for regression. We want to find a line that minimizes the squared error, because squared error is a reasonable thing. No line, and if you have noise, no line would perfectly pass through all the data points in the regression case. And in classification case, no line or no hyperplane would separate all data points exactly. Some of the classes, some of the data points would be misclassified. The question is that how we want to measure how bad we are in misclassifying this. So now the question is from you, what loss function should we define? What's a reasonable loss function? Or what's the first thing that comes to your mind? Also on the chat. I mean, you can look at the next slide, but don't. Yes. So the answer is the Hamming distance between the predictions Y's and the target T. Okay, so that's good. So essentially, basically, you want to count the number of differences between what one predicts 1, the other predicts 0, essentially. Okay, so that's good. Which would be the same as what we have on chat, counting the number of misclassifications. So that's good. So essentially, we can say what matters is that how many errors we make. Let's just minimize that. So now the idea is that we define a loss function and then try to minimize it as with what we did before. What loss function is suitable, as you suggested, we can count the number of misclassification. So what is defined is that we define something called 0-1 loss, which would be equivalent of the number of whether something is classified correctly or not. So this is defined as like this. So loss function will point for predicting Y when the truth is T. The loss function would be 0 if Y is equal to T. It would be 1 if Y is not equal to T. So this is exactly the same as you said, misclassification, just this is for one data point, or it's one dimension of Hamming distance that you mentioned. This also can be written as identity of, it's written here, of whether Y is equal or not equal to T. So if Y is not equal to T, this counts as 1. If they are the same, then there wouldn't be any loss. So this is just a kind of more compact mathematical notation. So this is, of course, for one point. Now we count for all the training points, and that would be our cost function. So that would be like point was lost, this is the cost. So J would be average or sum of our training data. And this would be essentially, we write it as 1/n of summation of our n data points of 0-1 loss, which can be also written as whether identity function of whether yi is the same or different from ti. So this is our misclassification rate or error. And which we mentioned before, I guess, in the first lecture, but maybe it wasn't formally defined. So I kind of defined it in English, but this is misclassification error rate. The question, however, is that now, okay, so we chose a loss function. Now we want to find W that optimizes it. The problem is that in general, this can be a very hard optimization problem. It can be NP hard. And this is due to the fact that this function, this 0-1 loss function, is not a very nice function. It is, as I kind of argue in the next slide, in a little bit more detail. So basically, in this slide, I'm arguing that why it is not a nice function from the perspective of doing gradient descent. Like if you want to do gradient descent using this loss function, 0-1 loss function, that would be a challenging problem. Okay, so minimum function, we knew that. It's a critical point, so we can try to do gradient descent. So let's try to find the critical point of 0-1 loss function. So consider 0-1 loss function of y and t equal to 0. So I just assume that the target is 0 for simplicity and write this 0-1 loss function as a function of w, of y. So remember that y is actually a function of weights. So it would be, we essentially what we do, okay, I have it here. So we compute z, which is w transpose x, and then pass it through thresholding. And whether it is positive or negative, okay, so I guess this is a bit problematic here. I need a thresholding here too. Yeah, okay, so this needs a thresholding too. So this is just a linear function, but I need to threshold it first to get y. So this would be correct. So there's a thresholding step too that I kind of missed here. It shouldn't be that. So now we want to find the gradient of it. What we do is that, well, we want to compute the gradient with respect to one of the weights. So this is a loss function. We compute the gradient with respect to one of the weights, which can be seen as gradient by chain rule. We can write it as gradient with respect to z, and gradient of z with respect to a partial derivative of z with respect to one of wj's. So the relation between z and wj is easy because z was a linear combination of w's. So that would be that wouldn't be a problem. But if we write the gradient, the partial derivative of loss, as a function of z, you can convince yourself that the loss function as a function of z looks like this. So it would be positive here at the threshold value of 0. And when the values are z's are negative, the loss function would be 0. Remember that here I assume that target is 0. So if z targets are 0, which is basically the negative case, if z's are negative, there wouldn't be any loss. If z's are positive, there would be a loss, and the amount of loss would be +1. So this is shown here. So this is the loss function as a function of the z. Now we need to compute its partial derivative with respect to z. So what would be the partial derivative of this function? Zero, except at one single point that it's not differentiable. So what is the problem of having partial derivative of 0? It means right, so it cannot be updated. Yes, so on the chat we have 0 everywhere except the threshold, which is the function is not differentiable. And the issue would be that essentially we don't get any gradient information here. If our z is here, we don't get any gradient information through this chain rule. So we can't know what direction we have to go in order to decrease the loss function. So this kind of intuitively shows why gradient descent would not work in this case. Okay, so this is a 0-1 loss is a reasonable loss function in the sense that it encodes our belief that classification error is important, but we can't optimize it. So what we do is that we use another loss function, which is easier to optimize. And if we optimize it, the solution would be a good proxy to optimizing the original loss, which is 0-1 loss in this case. So this is known as a relaxation of a loss function with kind of some nice surrogate loss function. So what is kind of important here is that this surrogate loss basically means a loss that is used instead of another original loss, which is, for example, difficult to optimize. Okay, so let's get to this, try to find some loss functions. So we go through that. That was our first attempt. This is attempt 1, which wasn't successful. Let's go another attempt, which is we do something like linear regression. Okay, it takes a while for you to get up. Okay, so this attempt 2 is which use a squared error loss function and then see how it works. We know how to fit a linear regression model using squared error loss. So maybe we can use the same squared error loss instead. So we have Z as W transpose X plus B. Squared error loss was the difference between Z and T. So it doesn't really matter. We can argue that it doesn't really matter whether the targets are binary or not. I mean, they are 0 or 1 or -1 and +1. So just consider them as a real valued number. And then we compute this, like we minimize this loss. We find a way that minimizes that loss function. And then at the end, in order to convert our solution to be binary, we do a threshold. Like if Z becomes larger than half, we say the output would be class +1. And if it becomes smaller than half, we say the value would be -1. But there would be a problem. And the problem is that, so this loss function, essentially, you can think of it as it penalizes you a lot if you make a prediction with a very large Z. So say you predict Z equal to be 5. And suppose the true target is 1. Suppose the true target is 1, and you predict Z to be, okay, 1, just start from 1. So what does it mean? Then your cost function would be T minus Z squared, which would be, in this case, would be 1 minus 1 squared, which is 0. So this is a perfect classification, perfect fit. But suppose now you have Z that is equal to 5, which basically means that your point is kind of has a large margin, or your linear model with high confidence says that your output would be positive. So in that case, you get 5 minus 1. And if you take the squared value of it, that would be a large value. So actually, when you are very positive about, and you know that Z being positive is the correct answer. But if you're very positive, then you are being penalized a lot. So this is kind of the argument that this loss function may not be a very good loss function, even though and does not work even if your linear model is performing correctly. Okay, so this is squared error. So that's a problem of the squared error. What was the source of the problem? You can argue that one of the source of problem was that your prediction, your model was predicting something larger than a range of 0 and 1. So what if you squish everything to make sure everything is going to be between 0 and 1? because at the end of the day, you want to predict either 0 or 1 or some value in between. So what we can do is that we pass the function, our output of our linear model, the z, to a function that makes it stay between value of 0 and 1. So this is our another third attempt. So this is z. If z is very positive, we say that the output of our model y would be +1. If it is very negative, -6, the value would be 0. But in between, the behavior is kind of nice and smooth. So this function that I'm showing you, this behavior is called logistic function, which is defined like this. That's sigma of z would be 1 divided by 1 plus e to the power of -z. And you can convince yourself that if z is very positive, then this function converges to 1. If it is very negative, it converges to 0. So let's call this function, or let's use this function to make sure our values stay between 0 and 1. So how does it work? So again, we compute z as before, but then pass it through this logistic function to get y, and then again use the same squared error loss function as our loss function. Okay, so the problem with this is that again we lose some gradient information. So let's see how it works. Suppose this is so I'm plotting the loss of squared error loss as a function of z, assuming that the target is supposed to be 1. So the target, when the target is supposed to be 1, what type of z is? Do we prefer positive z's or negative z's? So if yes, exactly. So the loss should be we prefer positive z's. So when z is large, then the loss should be small. So if we calculate it, the loss function looks like this kind of blue curve. So we see that it is 0 in this region if it's positive, and if it is very negative, so we are making a wrong prediction, then our loss function would be close to 0.5. So this is good. It just shows the right. It has the right order of which side is good or which side is bad. But there is a problem there. The problem is that if, suppose we are predicting z to be, okay, the problem is that suppose z is a very negative number. So it is an incorrect value. Now we want to do gradient descent in order to update it. But if we do the gradient descent, so the loss function, so if we are at this point, for example, z is equal to 4, the gradient is the slope of this loss function as a function of z. So this term of the gradient. So we have the loss function, partial derivative of it with respect to w. So it would be partial derivative of loss with respect to z. Output of our model, partial derivative of z with respect to w. The second term is okay, but I'm just looking at the first term. And the first term says that if z is very negative value, then this partial derivative is almost equal to 0. It's very flat. Like as we get to this point, this is almost flat. So the gradient or partial derivative would be almost 0. So what's the result? What does it mean? It means that if our prediction is very wrong, then we don't get any gradient information to update our weights. So even though using this logistic function, activation function, is a good idea, but this choice of squared error loss is still problematic for us.
So, I have a question.
Yes.
You focus on the negative values,
Mhm.
use the gradient for that. But even for Z being positive, so we know that Z being positive is a good thing.
Mhm.
But we still want some information about the loss function. We still get the gradient as well.
So that's the thing. But if it is positive, both of them are positive, we don't need to update anything. Yes.
Can I solve this problem by normalizing data?
Normalizing a delta.
Yeah.
What is delta?
Data.
Data. Not really, because this is not a problem of. I mean, this is mostly a problem of if our linear models become very confident or very wrong, we don't get gradient information. I guess what you're referring is that if you kind of make x's all between certain values, then we never become very confident, or very wrong in some sense. So that maybe helps a little bit, but we actually want our model to be very confident. And this kind of prevents that to happen, because we can always make W's larger, even if x's are fixed size, like if you bound them, if W's become very large, that Z can become very negative or very positive. And then you would be in the same situation. Okay, so this is another attempt, which we call it logistic regression. And that's a kind of strange name because it doesn't have much to do with regression. But okay, so this other attempt is that we say that we define a new loss function. We use the same logistic model or activation function for squishing the values of our prediction between 0 and 1. But then we somehow interpret our prediction as a probability. And we say that if we are very confident when actually we shouldn't be, because we are the wrong decision, we should be penalized more compared to the case that we are less confident. So let's just see, for example, what it means. Say if someone says that Clinton would win the election with 99%, that person's classification, that should get a larger loss compared to a person who said that Clinton would win only with 90% chance. Now, Clinton didn't win, so both of them should suffer some loss, but the loss of the first one should be larger than the second. So the way that it works, we can use some loss function, which is called cross entropy loss or log loss, which captures this intuition. So let's see. So this loss function says that if I predict y, which is between 0 and 1, assume it has a probabilistic interpretation now, but the true is t. If t is equal to 1, the loss would be minus log of y. And if t is equal to 0, the loss should be minus log of 1 minus y. So I mean, this, you need to kind of draw it to see how it looks like. If we draw it, it would be like this. So when t is equal to 0, so we want to predict y is to be close to 0, right? If t is equal to 0, it is negative case. So we want to predict y to be close to 0. In that case, if you're close to 0, then loss would be small, but then loss becomes larger and larger as we predict the wrong direction. So if we predict the y says that y is close to 1, then that would be a big loss. And why the opposite case, when the true prediction is supposed to be 1, positive case, if we predict y equal to 1, that is fine, there's no loss. But if we predict y equal to 0, we should suffer large loss. And the behavior is defined by this kind of logarithmic function. So this is called cross entropy loss or log loss. And this is the formula. And actually, it is good to convince yourself that I can write it compactly as equal to minus t log y minus 1 minus t log 1 minus y. So it is not difficult to see because t is either 1 or 0. So either of these cases, it acts like a switch. If t is equal to 1, this term only is on, and this term is off, and vice versa. So this is kind of like a very compact way to write these switching cases. So this is our logistic. So this is called, okay, so logistic regression would be the case that we use a linear model. So this is a linear model. And we use that activation function, logistic activation function that we have. So we make sure that all the values stay between 0 and 1 through that quotient function. And then the prediction, which would be y, goes through this cross entropy loss function, which would be, as I said, minus t log y, 1 minus t log 1 minus t. So if that's the case, this would be called logistic regression. And the loss function as a function of z looks like this. So here it is drawn for the case that the true target is supposed to be t equal to 1, so positive. So in the positive case, we are not supposed to suffer anything. In the negative case, we suffer some loss. So in the positive case, we suffer something, and in the negative case, we suffer some losses. And how much we suffer depends on, I guess they're very exciting. How much we suffer depends on how negative our prediction Z is. And you see that the behavior asymptotically looks like a line. So here, this dashed line is a line and kind of shows that the cross entropy loss with this linear model, the logistic regression, essentially, it's in the negative side, it becomes like a linear loss, more Z, more negative, more loss, but in linear fashion. In a positive case, it never becomes 0 exactly, but it just converges to 0 in the fashion that is shown here. Okay, so so there is this slide. I guess I skip it, just saying that if you want to numerically compute it, numerically it might be process might be a bit numerically unstable. So there is a better way to compute it, like if you use Python or NumPy, there's a functions that you can do it in a more numerically stable way. So you can use logistic cross entropy function. And maybe the other thing that I want to mention here is that just consider all the loss functions for classification that we have seen here. So here they assume the target is equal to t equal to 1. So we want z to be positive. So there shouldn't be any loss when z's are positive. When z's are negative, there should be some loss. So the blue one is the 0, 1 loss that we have. When things are positive, there is no loss. When things are negative, no matter how negative it is, the loss is always 1. And then we have least squares loss, which is 0 exactly when we predict value equal to 1. So if when y becomes 1, the error is 0. When it's negative, the error would be large. The problem with it is that when it becomes very positive too, it becomes large too. Then we have logistic activation function with least square loss function, which if we visualize it, it looks like this line or this curve, which kind of loses the gradient information when z becomes negative. And then we have this logistic cross entropy, which would be this red curve that is on the positive side, there is still loss, but the loss becomes smaller and smaller. And it is kind of encouraging us Z to be very positive because the loss would be smaller when Z becomes very positive. And when Z becomes very negative, it suffers a loss, and the way that it suffers the loss is linear. Okay, I think that's enough. We are almost done with the main part of classification, but still, I guess probably need 1 more hour to finish it. So I try to finish it, this one, and then start the bias variance one on test. Okay, thank you very much. Bye.